Today I'm going to finish what I started about credit risk, and I'm going to get closer and closer to how these things are done in practice. I'm going to become, from a mathematical perspective, dirtier and dirtier, and from an applied perspective, more and more useful in everything that we're doing. The plan for our walk today is we're going to climb a very steep hill. We're going to see very advanced credit models and this and that. But then we're going to see how they're applied in practice. And you will see that when you apply them in practice, there's lots of room for simplifications, because we will also see how difficult these things can be in real situations with real institutions, with real portfolios of clients, and so on and so forth. So, and that would be the end of this. I'm going to start with the, basically with, remind you of something that we saw last week. This was the cash flow valuation formula for a zero coupon bond with a default. And here I want to draw your attention to the variables that we considered. So V was the value of the bond, N was the notional of the bond, R is the interest rate, Q was the probability of solvency, R was the recovery rate. And what that told us is that the probability, the value of this bond was the expected return on the one hand, and then the expected recovery in the case of default on the other hand. That's what it was. And we applied this in the context of sovereign bonds, bonds issued by governments. This applies everywhere, but we saw that in the context of bonds issued by governments, and I specifically mentioned the case of the Greek bond in the context of the European Union, which is a very good testing ground for these theories because of the fact that it's the only region on Earth that has the same currency being used by different countries with different credit ratings. Okay, it doesn't exist anywhere else. And when we do that, we see that there's really a superposition of three different factors. We only focused on one last week. We focused on the concept of default, and we spent a lot of time on that, and we saw the Markov model for default, and that's what we did. That was last week. We focused on that. But overlaying that factor, there's two others. One is the exposure. Of course, for a bond, this is constant. The amount of money which is owed to you or you owe is constant. But remember the example we saw with Goodrich. That was a fundamental concern. In fact, it was the fundamental reason why that deal went through, and that was because exposure and default, they were related to each other and they went opposite to each other. So when the probability of default goes up, the exposure goes down. Remember that? So this is something which is inherent to credit risk, and we need to understand it. And understanding that is hard. It's hard because we need to understand the relationship of two very elusive concepts, one which is exposure and one which is default. And they are difficult because they depend on completely different things. Default depends on your counterparty only, but credit exposure typically depends on the market. If we go back to the Goodrich example, Goodrich has a credit quality which affects the probability of default, but then the interest rate markets follow their own process. We found the relationship, a negative correlation, and that is what made the deal happen. But oftentimes we may not be so lucky, or there may be a relationship that we are not aware of, and that makes it difficult. But then on top of that, there's a third element, and that is the recovery rate. The recovery rate is something which I just took to be a number last week today we will see what we can do to develop that into a more realistic setting. So this is the challenge. This is why credit is complicated, because it mixes things that have to do with, on the one hand, your counterparties. On the other hand, the markets. And on the other hand, this recovery rate, which is almost a legal overlay. Because in the case of default, what happens in the case of default? Liquidators take over. Liquidators will take possession of the counterparty's assets, and then what? They use them to pay who? So who's paid first? No. Taxes. The government. Okay? The government is always first. Who's paid second?
That is the creditors?
No. Liquidators. Okay? The people doing the liquidation get paid next. Then comes the creditors. But the creditors are not all the same. Sometimes there are creditors that have advantages. They are first in line, so to speak. They are typically called senior creditors. They are first. Once they have satisfied all of their needs, if there's anything left, then you go to the next wave of creditors, which could be the junior, mezzanine, and we will see this terminology today, right? This is called the capital structure of your debt. Not everybody has equal rights to your assets. So government is first, liquidators are next, senior creditors are next, junior creditors are then, mezzanine creditors are then, and then shareholders are last. Shareholders never get anything. That's why you go bankrupt, right? So that has to be modeled too. So look at that. We have three factors, all of them difficult in themselves to model. But to do this properly, we should be able to model this not only individually, but jointly. And this is why credit is so hard. And on top of that, there's something else that I have not mentioned, which is markets will continue to do their thing, and beyond the credit event itself, there are things that could that also affect your portfolio, even if your counterparties do not default. We're going to see all of that today, but it's so complicated that we're going to have to start taking shortcuts here, there, and everywhere. The whole problem is massive, very hard. When you're at a bank, you will probably be addressing a lot of these issues by provinces, by focusing here, focusing there. Once you get more senior into the bank, then you're going to have a more wholesome approach to all of these topics. And we will have a first row view of how complicated these things can be, but then we're going to end with a fairly simplified view of the world that will be able to make it work, okay? So that's the plan for today. Yes?
Quick question. In that equation, is the recovery rate defined with respect to the principal or the...
It's a percentage. Here's a percentage. It's a percentage. So it's relative to the principal, yes, it's a percentage.
If it's relative to the principal, why do we need to discount that term? If this thing defaults and we'll get a percentage of the principal.
Because we're doing the value today of the future recovery rate. If I'm going to recover $10 million in 5 years, I want to know how much that's worth today, that's all. Well, no, this is a zero coupon bond, so this will happen at a unit of time, which I did not include there, whatever that is. So say this would be like for a year, for example. Then I'm just discounting that a year to today. Okay? Yeah. as we've learned, value has two variables, currency and time. So that would be the one corresponding to the time element. Here I'm taking a unit of time, say a year. Okay. If you want to make this time dependent, then I would multiply R by T, and I would include Q sub T. Q would be the probability of solvency at time T. And R will be the recovery rate at time T, in case R is also time dependent. And then that's how these things get more and more complicated because of the variables and how all these quantities relate to all those variables. Okay, so how many variables in this equation? 1, 2, 3, 4, 5. Right? Modeling 5 variables. You can say, well, I don't need to model notional. Yes, that's for a bond. But if you look for a swap, for example, we'll have to model the value of the swap. So there's 5 variables, and modeling them is what makes credit risk complicated, because they will depend on many different things. So I'm going to go step by step. I'm going to start with credit exposure. Credit exposure is the maximum loss the portfolio can experience. The maximum. Okay? Now, of course, the maximum could be, it will change from point to point, and it has to be with a certain level of confidence. There are situations where the maximum you could lose will be infinity. If someone owes you, for example, the value of a certain stock, in principle, it would be infinity. So what does maximum mean? These are random variables. So we look at the maximum with a certain level of confidence. That's what credit exposure is. So credit exposure is a quantile at a point in time. Okay, we're going to see an example. This is my favorite example. This is how the exposure of the Goodrich swap could look like. Okay? I don't believe that these numbers are realistic. I probably just made them up with my finger. I don't know. But it looks like that. What do we see there? When we start with my swap, the swap is issued at value 0. So this would be the value of my swap. So my swap will have now a value of 0, and I know that for sure. And then as time goes by, uncertainty will make the value of the swap perhaps increase, perhaps decrease. So if I'm looking at the quantile, I have 2 quantiles here. I have the 95 and 99 percentile, I believe, okay, of the swap. Then as I have the time go by, I can see that the uncertainty of interest rates will make the value of the swap go up or go down. If I'm looking at credit risk, if I'm looking at what I can lose, I worry about what? I worry about the value of the swap going up. Remember, if the value of the swap goes down, we're happy. Because if my counterparty defaults when I owe them money, it's better than they default when they owe me money. Right? Okay, that's the asymmetric way of thinking for credit. And every time a payment happens, then my exposure comes down. Right? The value of the swap will come down every time a payment happens. That's why we have this jagged shape, that every 6 months, once you get payment, you get some relief, right? But this is not the credit exposure. The credit exposure is the highest number in the future. So today, if I want to know the 99% exposure of my Goodrich swap, the answer is not 0. The value of the swap is 0. But the exposure would be very close to 70 million. You see? The 95% credit exposure will be something close to, I don't know what that is, 42 million or something like that. So the credit exposure is the maximum amount I can lose at the worst possible time with a confidence level. Otherwise, the number will be infinity, right? That's the credit exposure, is how bad things could get. Case of a mortgage. The mortgage is, well, if you assume home prices are constant, if you assume that what is the largest amount you can lose? Well, it's going to be what has been loaned to you. Is the highest possible value. If it's a fixed rate or floating rate mortgage, might be slightly different, but mortgages have fairly predictable credit exposures. Swaps don't. Swaps can have very unpredictable credit exposures. And certainly the value being zero today is no reason to think that a swap is not going to give you a credit risk profile, okay? Understand? That's credit exposure, the highest number you can lose at any point in time. Okay. Next comes this object we call recovery rate and its related element called loss given default. So when default occurs, there is some sort of recovery. We just went through that. The assets of the defaulting company will be used to pay the government, pay the liquidators, and then the creditors. And that means that there is a chance you get some of that back. The case of sovereign risk, there's no tax considerations. They don't pay tax themselves. The liquidators do get paid for sure, and whatever is left, that goes to the creditors of the nation. We're going to use two related terms. One is called the recovery rate, is how much you get, and that's a number which is expressed in percentages, and the number ranges between 0 and 1. We don't know what it is, but it is between 0 and 1. And loss given default is the opposite. It's what you expect to lose once default occurs. So they are related to each other because one is one minus the other. This is recovery rate. And right now it's just a vocabulary definition. We don't have any model for that. We don't know anything about that. You can assume them to be random. You can assume them to be fixed. This is part of your modeling assumptions. We're going to assume for the most part today that they're going to be constant, but at a beautiful, beautiful point of the lecture today, we will introduce the Merton model where the recovery rate will be given to us as a random variable, and we'll have to do nothing about that. It'll just be automatic. It'll be very, very nice. You will see. Here is some statistics. This is part of a very, it's two studies, one by Altman and others, and the other one by Lieberman and others. And I just want to walk you through this so that you understand some of the terminology related to credit. On the left-hand side of this table, you can see something called the seniority class. And then we have senior secured, senior unsecured, senior subordinated, subordinated, junior subordinated. What does that mean? That means that there's different classifications for the liabilities of the company in this case, okay, or the counterparty. Senior secured is the safest of all of the creditors. They are the first ones to get paid, and also they are secured, meaning there is some asset that guarantees that payment somehow. For example, the case of a mortgage. The bank likes to be first to get paid, and the house acts as your security, right? So that'll be an example of that. The next one would be senior unsecured. For example, that would be a line of credit, which is unsecured. Or in the case of a company, that would be a bond issue, which is backed by the assets of the company, but no specific asset. Then you have senior subordinated, which is, gets paid after the senior and is subordinated because it's subordinated to the senior unsecured. And then you will have the subordinated, which has less priority than the senior, and then junior, which has the last amount or the least amount of security or priority in getting paid. All right, these are the 5 classes. They were used in this study. Let me look at the study by Altman. No particular reason. It's a friend of mine. So, so they looked at 85 such deals, and they saw that the average recovery rate was 57%. Okay? With a standard deviation of 22. That means that the recovery rate would range between 30 and 70, something like that. It's just to give you an idea, right? Then when you go one step down, the average goes down a little bit and the standard deviation goes up a little bit. When you go all the way down to subordinated, that is where the average recovery rate is 30%. The standard deviation is 20. So there will be cases where you get nothing back, and cases where you actually get a pretty good return, pretty good recovery of 50%. All right? They did not look at junior subordinated. The case of Lieberman, they did look at that, and the recovery is smaller. You understand? So this is something. You can imagine how this thing was done. They took about 500 of these cases, and they say, well, which one is this? And then I guess they hired some students to organize all the data, and then they got the table. Yes? That's great. This is very good from a historical perspective. If you are dealing with a real portfolio, how do you use this? We will see. Okay? In principle, you can say, well, let me do something. I'll just, which one is this? This particular debt issue that I'm going to have in my portfolio is senior unsecured. So I use the average. I use 47%, and then I go home. That would be, right? You can do something fancy. Say, well, no, it's 47%, but it has a standard deviation. I'm going to put a Gaussian model on that. You can do that too. We're going to see today, actually you're going to solve problems where this thing will be explicitly addressed. So not to worry. Yes?
Just about the scenario class, when dissolution happens, is it like, say, senior secured, is like all the money owed to them is paid out before like senior unsecured?
Yes. Yes, they get paid first. So senior unsecured only gets paid after the senior secured has been paid.
It just seems a little strange to me that the numbers are so close then, right? Because like because that like in that sense, would that mean that for senior unsecured to get paid anything, senior secured has to have already had a 100% recovery rate?
Correct, has to have been paid everything. So what my guess would be, for example, that in 50% of, imagine this, most of the time, the security was enough to pay both secured and unsecured, right? Then you have very similar statistics for the two of them, right?
Yeah, makes sense.
Yeah, okay. So to develop models for this, I'm going to have to be a little bit pedantic. I'm going to introduce things. Mathematically, they may look very daunting, but they are very simple to understand. The first thing I'm going to do is I'm going to introduce something called the stochastic default process. This is a very simple process, which is equal to 0 if you're solvent, and it jumps to 1 when you default, and then it stays 1 forever. So it's 0, you default, goes to 1, and then it stays 1 forever. It only has two values, 0 and 1, and it changes from one to the other only once when you default. And we don't know what that is, so that's what's a stochastic process, okay? Then think that the probability of default would then be the expectation of this process at a particular point in time. Why are we doing this? I'm doing this because I want to have to understand or model the relationship between the value of my portfolio, which is time dependent, and the credit quality of my counterparty, which is also time dependent. So that's why I do that. I'm not introducing anything new. We spent all of last week talking about the probability of default, but now we just look inside and say, well, the probability of default is the expectation of this process, which was implicitly in our conversation last week. Today is going to be explicit. Don't be scared by the expression that you have here. You've seen worse. Okay? Yeah, you've seen worse. So with that, I'm going to define my first mathematical object to understand this, which is the credit loss process. It's going to be the multiplication of three things. It's going to be the multiplication of my default process. So if there is no default, the credit loss would be 0 because I'm multiplying by 0. If it's 1, it'll be what? It'll be the credit exposure times the loss given default. Now at this point you may think, oh, the credit exposure, I'm overestimating now the risk because the credit exposure was the worst value this portfolio could have in the future, right? So maybe you lose less than this. And yes, that's what it is. It's an overestimation. As we will see today, a lot of these things are done for risk management purposes, sometimes for trading, but the trading is going to have a different approach. So for risk management purposes, you want to follow this approach. It's the most conservative one. And then loss given default is a complete unknown. We have no idea what that's going to be, right? It's not something that you can look up in the newspaper. You typically only find out this at the time of default. Once the liquidators go through the assets of the company, the obligations, and someone tells you, you know what, good luck. You're going to get 30% back. Okay, but you don't know. This is fairly intimate information. Understand that? I'm multiplying three very different processes together to have our credit loss process. The first one depends on the counterparty only. The second depends on the market risk and the actual portfolio that we're looking at. And the third is a situational random variable, hard to model. Understand? This is what credit risk is made of, three very distinct elements. And we're going to define the credit loss variable like this, knowing that it's an overestimation because the credit exposure is an overestimation. All clear? Everybody? If I have several counterparties, what do? I just add them up. Okay? All right. Now, the credit loss distribution is often very complex. It depends on a lot of different risk factors that we may not know. Now, let's follow this approach Markovitch style. You may not know what that is. We'll see that next week, which is we're going to try to assume that the mean and the standard deviation is a good way to grasp some of that. We will see it's not going to be very useful, but it's a way to start. So we're going to look at the expected values called the expected loss. That's the amount of money we expect to lose. And the other one is the standard deviation, which is oftentimes called the unexpected loss. It's the loss in excess of what you already expected, okay? And the distribution typically looks like this. There's never credit gains. Although we'll say something about that in a minute, okay? There are credit gains, but at this juncture of this lecture today, there are no credit gains, which means that my credit loss distribution, to begin with, it's asymmetric. It only lives on the positive loss x-axis, nothing on the negative one. Right? So forget about a Gaussian model, won't work. Right? And it typically has a fairly long tail. It has events which are very large and more frequent than you might expect. This is just a characteristic of this. Maybe I give you an analog, something that we saw here very briefly, but you may have seen, you may have studied ruin in the case of stochastic processes. And they remind you of one thing, which is that the hitting time of a random process has an expectation which is infinity. So you will hit something, but you may have to wait forever. These are examples of situations where these extreme events could happen. They could be very large, and they could happen very infrequently, but they can be very large. Now, to understand this, we're going to follow our first approach to this is very simple. The mu is the mean, You see it there, that's the expected loss. And the standard deviation would be the variation from that mean. That's our first way to tackle this. But as experienced statisticians that you may be, you already recognize that this is going to be a very poor description of this distribution, right? The mu and the standard deviation for an asymmetric distribution with fat tails is probably not going to be very useful. We're going to try to do better. But this is a way to start. It introduces a very interesting perspective, which is the expected and unexpected loss. Don't dismiss this, okay? This is, like I said, this is not very accurate, but it's very intuitive and very useful. So don't dismiss it. It's not as bad as it looks. The way to approach this correctly is what's called credit value at risk, or credit VAR. And related to that is the worst credit loss. So another vocabulary definition. This is all definitions. The worst credit loss and the credit value at risk are related to this thing called value at risk that we saw a couple of weeks ago. The worst credit loss represents the credit loss that I could have with a certain confidence level. The credit value at risk is the difference between that largest credit loss and the expected credit loss. So the worst credit loss is a quantile. The credit VAR is the difference between the quantile and the expected credit loss. If you want to find an analogy, the credit VAR will be similar to the standard deviation because it looks at the variability minus the mean. Okay? And there's a regulatory reason why we think like this. You will see this is how you always think about credit. Credit will always have two components. We called them earlier expected and unexpected loss. Simplistic but intuitive. Now, the expected loss is still there, but I'm removing the unexpected loss by the credit value at risk. And in practical terms, this is going to have yet a different name. One is going to be called credit reserve, and the other will be called regulatory capital. But they're all the same concepts. Okay? So when I look at something like this, the credit value at risk is going to be unrelated to the unexpected loss, to the standard deviation, typically much bigger. Typically much bigger. It's a quantile. For a distribution like this, the standard deviation, which for a Gaussian gives you the quantile perfectly, here it will typically underestimate the quantile. The quantile will typically be bigger. The worst credit loss or the credit VAR will typically be bigger than the standard deviation. Okay? The worst credit loss typically sits around there. We're going to see examples of that. Actually, no, we'll see one example of that. I don't have time for a lot of examples, but that should be good enough. Oh, actually, sorry, something very important. I went very quickly through this, and I want to stress it again. So the worst credit loss could be there. Like I told you, typically it's a lot bigger than the unexpected loss. But remember that the credit value at risk is the difference between the biggest loss and the expected loss. In other words, what we're doing is a type of risk accounting. The worst credit loss, we're going to divide it up into two parts. One part is the part that has to do with the actual loss, and the other is the part that has to do with what we already expected to lose. That's the type of risk accounting we're doing. Understand? We break up the worst credit loss into two parts. And they will be treated differently. The dollar amount might be the same, but they will be treated differently. We're going to do a trade today. And in that trade, I think you're going to understand that very well. Let me give you a very simple, well, it's not an example. The example is coming later. But this is just is the definition with numbers. So when I say that the worst credit loss, 95% worst credit loss of a $5 million is $5 million of a certain portfolio, means that the probability that I lose more than $5 million is 5%. That's what it means. That's the definition of the quantile in English. A daily credit value at risk equal to $5 million means that the probability that I lose $5 million more than I expect is only 5%. Okay, we're going to see, there's one example. This would become clear. Let me now talk about the economic credit capital, which is the way to do risk accounting. There's two objects, credit reserves and regulatory capital. Credit reserves are set aside to absorb expected losses. Perhaps you're more familiar with an insurance company. An insurance company sells policies, and they charge premium for that, right? When they charge the premium, of course, you don't know what goes into what, but in the premium, there's a piece of that premium which is what they already know they're going to lose. And there's a piece of that which is, well, this is to collect additional premium because there's going to be deviations against them, probably, from what they expect to lose. Okay, so here we're dissecting that. The expected losses is what we expect to lose, and capital, regulatory capital, is typically designed to absorb unexpected losses. This is the one that worries regulators. Expected losses is the one that worries business developers for a bank, for example. Regulators will be more concerned with unexpected losses. So worst credit loss measures the sum of the capital and the credit reserves. And credit VaR, therefore, is the right measure of regulatory capital. And it could be calculated over a one-time horizon, but sometimes you can do this monthly, for example. Losses come from defaults, but from a regulatory perspective, losses can come from defaults or actually from migrations. Imagine that my counterparty gets downgraded. It does not trigger a default, but now my portfolio is worth less, and that could increase my regulatory capital. We'll see an example of that. Okay, so in the most general sense, the expected credit loss is the expectation of my credit loss random process. Let's assume that the factors were independent. If the factors were independent, then the expected credit loss would be the what? The expectation of each of those, but they're independent. The expectation of the product is the product of the expectations. So in that case, that will be the expectation of my default process is the probability of default. We already saw that. That will be the expected exposure, and then I would have the expected severity. So there I would get that table from Altman, and I'll say, well, where am I here? Okay, so that's my expected value, and that would be it. That's a very fast way to get my expected credit loss. Now, I want you to do some work now, because we've seen a lot of things, and now this has become very theoretical and this and that. So I have an assignment for you. I would like to give you 5 minutes to do it, right here. Okay, I'm not gonna grade it or anything. Don't be afraid. I can see your eyes going like, what? Unexpected? No. This is really an attempt that you understand what I'm talking about. I've introduced a lot of different concepts, a lot of definitions, and this and that. I want to wait for you as you climb up this hill. I'm gonna give you this example. So in this example, I'm gonna do two. Sorry, you are gonna do two. I just wait patiently 10 minutes until you do it. I want you to try, okay? The first has to do with a commercial mortgage. And this also gives me a chance of telling you stories, because I want you to understand credit from a very, very practical and intuitive perspective. Everybody knows mortgages, right? I have a mortgage. Anybody else has a mortgage? No? Well, one day you'll have a mortgage. That'll be a very good day for you, okay? Something you should be looking forward to, yes. It means you have a home or something. But a commercial mortgage is what? What's the difference between a residential and a commercial mortgage? An example of a commercial mortgage is a mortgage to build a shopping mall, for example. I'm interested in a shopping mall. I mean, it could be an airport. I'm not interested in that. A shopping mall is very, very interesting. What happens when you get a mortgage on, on a residence? You live there, right? It could happen that you lose your job, something happens, and then, well, you can't pay. And then the bank will take your home. But what happens if a company, say, buys a shopping mall, gets a $100 million mortgage, and the company cannot pay? What happens? Typically, what happens is this default doesn't happen because they lose your job, and typically this is the result of a very long process where they have extinguished all of their credit reserves, where they have done everything they can. They've delayed maintenance as much as they could. So that means that when there is default on a commercial mortgage, the recovery rate is typically very bad. On a residential, it's very good. I mean, you don't destroy your home just because you can't pay. But businesses would do that. They would do whatever it takes to, if they could sell the tiles off the wall, they will do it, right? Understand? It's an exaggeration, but you understand what I mean, right? So, when you get it back, maybe the sewers don't work, maybe this doesn't work, they didn't maintain the electricity and something blew up and a section of the shopping mall is burnt even, who knows, right? That's a commercial mortgage. So let's model that with what we've learned. That's the first assignment you're going to have. To model that with what we've learned. I want you to feel powerful after you do this. For that, I'm going to give you a very, very simple model. Very simple, but very powerful. There's there's power in simplicity, right? Sometimes complexity is just, you know what I mean. So let me give you some numbers. Imagine I have a commercial mortgage, shopping mall is the collateral, and the deal, the mortgage is $100 million because it's easy to multiply by 100. It has an expected probability of default of 20%. Remember that there was this expected, there was this default process there? The probability of default was the expectation, right? But the process itself can have also standard deviation, right? So I'm not going to give you the process itself. I'm just going to parameterize that default process by saying that the expected probability of default is 20% and the standard deviation is 10, whatever that may mean. And then I'm going to give you an expected recovery of 50% with a standard deviation of 10%. So recovery could be 60 or 40. Very mild numbers, but what you will learn is the same. It doesn't matter what the numbers are. I just pick numbers which are very easy to work with. You don't need a calculator, in other words. So I want you to calculate, and this is my assignment. I want to give you 5 minutes to do it here, okay? I want you to calculate the expected loss in 2 ways. First way, assume the independence of recovery and default. By the way, the exposure is constant, it's 100 million. There's no need to model it, it's constant. So here we only have 2 factors, recovery and default. So X would be the expected credit loss in the case of independence between recovery and default, right? And now you're going to assume a negative 50% correlation between the default probability and the recovery rate. We call it Y. Notice that this is exactly what I told you that describes commercial mortgages. If the default probability goes high, the recovery rate goes down, right? And if the probability default goes down, you're in good shape. You maintain your building. That collateral is worth a lot of money. You take good care of it. That's the way to model that. Yes? Everybody understands that? Yes? That describes mathematically the financial description I gave you earlier, right? Yes? Oh my God, something in your, your faces speak a lot. It may look like you say nothing when you come to class. That's not true. You say a lot of things, okay? And suddenly your faces are telling me that you don't get this. Okay, I'll wait until you do why don't you write things down, then that may change. So I want to ask you first for your guess, and then I want to ask you to actually do it. What is your best guess as to the numbers x and y? I want to give you 4 choices. The first choice is that one is 10, one is 10. Second is one is 10, one is 20. The other one is 10 and 5. And the other one is 10 and 10.5. Let's use the intuition first. So A and C should not work, right? Why? Let's go to the financial intuition. Non-mathematicians would know that because we just went through this, right? If the probability of default gets worse, the recovery is worse, so that's very bad. That means that Y should be higher than X. Intuitive. Y should be higher than X, right? Now the question is how much higher? Twice or just a little bit? That's what you have to do. You have to do the calculation now. I want you to do this calculation. Now, there is a chance that you don't know where to start. Am I right? You don't know where to start. Okay, I want to walk you through this. I want you to discover this on your own. If I tell you, I know you're not going to learn. I want to discover this with you. I want you to be in a position where you can actually, oh, I know what, then you get, you will have to do a calculation. You don't need a calculator. You can do it by hand, okay? But what is the first thing we need to do to model this? I would say the first thing we need to do is we need to understand what the 50% minus 50% correlation means between probability and recovery, right? Yes? Can we? Of course, we know you know correlation, but between default and recovery, what does that mean? How can we write a mathematical model for that? Yeah.
Isn't it the product of the two terms in expectation?
You're right. That's what correlation is. But
Minus.
Yes, you know the formula. Everybody knows the formula. I know that, right? How can you use it? How can you use this to model this situation?
Because they're not independent.
Yes. But how can you? So let me help you with that, okay? Because what you said is true. I know from, I do this every year. I know from experience that even if you know that, then you say, okay, now how to relate this to my mortgage? So I want to walk you through that. I want you to discover. Oh, by the way, there's many ways of doing this, okay? Many ways of doing this. You can write Python code, you can do a simulator, you can many things. But I want, you know my style. I want to go the simplest possible way. The simplest possible way. I don't care how many assumptions I make. That's the way to start always. The simplest possible way. We're going to do it with maybe 3 multiplications and that's it. And maybe 3 additions and that's it. Allow me, okay? I want you to be in the position that, imagine this was your final exam and you have to do this, otherwise you fail this course. I want you to feel that anxiety, because only from the anxiety you will appreciate the solution. Understand? Or even worse, this is what you have to do at work and you get it wrong, you get fired. That's worse than failing this course. Understand? And you have to do it. How would you do it? How would you do it? Okay, so let's start to model this. I'm gonna give you a very simple approach. We multiply the random variables, we use the correlation to calculate the expectation product, and that's one way. The other is the simulation approach. We simulate a process with the characteristics given. And then I'm going to follow the simulation approach. It's more intuitive than the analytic approach. Once you understand the simulation approach, then you can go to the analytic and you can do wonders and you can generalize this and that. But I'm going to follow the simulation approach. So I'm going to consider 2 equally likely future credit states from my counterparty, which will be labeled by the probability of default. One is 30, one is 10. Right? That gives me an average of 20, standard deviation of 10. So I've solved that, I've modeled that. Then I'm going to give two equally likely future recovery states, one given by 60%, one given by 40%. It matches I don't have the numbers in front of you, but it matches my expected 50 standard deviation of 10. Right? So I've created 4 possibilities for the future that are consistent with the assumptions in my statement. 4. That's it. You can all simulate 4 on a piece of paper, right? That's it. And which ones are they? 30 and 60, 30 and 40, 10 and 60, 10 and 40. Yes? That's it. So 4 states. We know what they are. So we can then go and multiply, and we got it. What's missing? Yeah, are these 4, I have 4 states, right? But what's the probability of each of them? Are they equally likely? Is it 25%, 25%, 25%, 25%? No, that would be they're independent. But they're not independent, they're correlated. So what are the probabilities of these 4 events? That's all we need to know. Because we have that, we can get the expectation. It's only 4 numbers, right? So what are the probabilities of my 4 events? The joint probabilities. We know they're not 25, 25, 25, 25. They'll all be independent. Correlation should model them differently, should do something to them, right? What? Let me help you out. Yes?
What you can say, assume the default probability is 10%, then you would, it's 50% more likely that the recovery is going to be the 60% instead of 40.
Say that again?
Like, maybe you can assume like one state, and then because you have negative 50% correlation, like the others. Like
Okay, So I don't understand what you're saying. So let me ask you a question, okay? And then to modify your answer. What's the probability that the default probability is 30% and the recovery rate is 60%? What's the probability of that? Given what you told me, I don't understand what you told me. So, but you understand what you said, right? So given what you said, how would you give me the answer to what's the probability of 30 and 60? I need that, right? I need the probability I need the probability that my default probability gets worse and the recovery rate gets better. I need to know that probability.
Is it 20%?
How do you get 20? The answer is no, but how do you get 20? It's not 25, right? We agree it's not 25. So let me help you out. Is it higher than 25 or less than 25? Probability that default gets worse and recovery gets better. Is that higher than 25 or less than 25? Use your intuition. Higher? Who thinks it's higher? Who thinks it's higher? You're alone. Who thinks it's lower? I think it's lower. Right? Higher probability of default and higher recovery. We just argued that when things go bad, that building is in bad shape, right? You're not cleaning the salt from the concrete. That rusts the rebar. That building will have to be demolished, right? Do you follow my example? So that number should be less than 25. Now he said 20. I don't know. Can you do that? You should know enough probability to do that, right? That's where the correlation comes up. I think your probability is a bit weak. Let me imagine I give you two coins, heads and tails, two coins, and I flip them, right? If the coins are independent, probability of heads, 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 tails, tails, heads, tails, tails is 25 each, right? What if the coins are correlated, 50% correlated? What's the outcome? What's the probability of the outcome heads, heads?
Like 3/8.
Oh, 3/8, is it? Maybe. Is it 3/8? I don't know. I know the actual number in with decimals. 3/8 is, let me divide. It's, I need a calculator. I know what the answer is. I don't know what 3/8 is. What's 3/8 in decimals? How much? 37.5. Yeah, that's the answer, yes. 37.5. You can all do that, right? It's 37.5%. I know that. I don't know 3/8. It's 37.5%. Yes? What's the probability of correlated coins? 50%. What's the probability of tails, tails?
It's the same.
The same. What's the probability of heads, tails?
It's 1/8. So
Well, it's 12.5%.
Yeah.
And you got it? You understand do you understand what I'm doing? You've all taken probability, everybody. Yes? You've done worse than this. Remember the probability course that you took? Yes? Was this hard? This would not be, would that be hard in the level of difficulty of that course? I hope not. I hope not, otherwise you took the wrong course. Right? But you understand what I'm saying? You need that, right? And I think it should be pretty clear that the probability is, well, is 37.5 and 12.5, right? Understand? So I think now you have everything because you have 4 events, you know the probabilities of each of those events, and now I'm asking you for the expected credit loss. So you can multiply the variables times the probabilities, right? Okay, that's what I want to give you 5 minutes. I want you to spend and it's going to be 5 minutes, okay, until 12:16. I want you to spend 5 minutes trying to do all of this on your own. Yes?
Wait, can you go back to the previous slide? Or the one, just where all the information is about all
Yeah. Oh, by the way, you have these notes on the website. I uploaded them this morning. So you mean this one?
Yeah, because I was lost the entire time because I didn't know what was what.
You didn't know what was what? Okay. So these are the 4 choices I give you, but of course now I want you to calculate y. By the way, there's no question x is 10 million, right? Because it's the expected exposure 100, the expected default 20, expected recovery 50. You multiply 100 times 20 times 50, you get 10. So x is easy, we know x. The question is what's y? Y is the one that uses the correlation. All right, until 12:16. I start with the correlated coins, 50%. We did the example already, but this is a Bernoulli experiment with 4 outcomes. And they need to satisfy the correlation equation, which is the first one, and then the marginal distribution equations, which are the other 2. And the answer to that is 37.5, 12.5, 12.5, 37.5. So that's we model the correlated coins first. That gives us the joint credit events we need to consider. So for the commercial mortgage, of course, the independent case is easy, just multiply the expectations. In the case of dependents, what you have to do is you have to multiply the exposure, which is constant, 100 million, times the 60% loss given default. This is not a recovery, it's the loss given default, times the 30% probability of default. That will happen with 37.5% chance, and same thing for the other three events. Probability of recovery goes, recovery goes up, so loss given default goes down. Probability of solvency gets better, so default goes down to 10%. That's 37.5, and then 12.5 and 12.5. The answer is 10.5 million. Okay? So yes, the commercial mortgage will have a slightly higher expected credit loss because of the effect of correlations. So that's what we've learned. We've learned how to attach mathematical measurement to these financial situations. Ready for the next one? Is this understood? Okay, let me go to the next one. The next one is the Goodrich swap. We're going to have a very, very simple description of the Goodrich swap, which is, and this is the swap between Goodrich and the Morgan Guarantee Trust. There was no Rabobank in this part of the swap. We're going to assume a total exposure of $10 million. Again, pick a simple number. 50% standard deviation. It's a swap, and the exposure for a swap can really vary a lot, okay, depending on where interest rates go. So a 50% standard deviation, or the way we think intuitively, is exposure can have two possible values of 5 and 15. And a default rate, which is 10% on average, but with a 3% standard deviation. So it could be anywhere from 7 to 13. And the recovery rate is fixed at 50%. I want you to calculate the expected loss in two ways. One is assuming independence of exposure and default, as before, call it X. And the other one is assuming a 50% negative correlation between default probability and exposure, which I remind you is what made this deal possible. That consideration that if that rates go down, Goodrich credit quality will improve. And that translates into precisely this relationship between exposure and default. Remember that? We discussed that at the beginning of class last week. So I want you to do that, and there's again 4 answers, A, B, C, and D. And as before, these two are not possible because we, again, financial intuition will tell us that Y should be lower than X in this case. Y should be lower than X. We should see a decrease in the credit profile of this particular dependence. Okay, so I give you 2 minutes to do this. 2 minutes, 2 minutes. You just have to do what you did earlier, but the notation is different. So 2 minutes until 12:22. So as usual, I want to follow the simulation approach, just as before. I'm going to assume 2 situations for default probabilities, 13 and 7, and 2 situations for the exposures, 15 and 5, and 50% correlation, negative 50% correlation. So the independence calculation is $500,000, no question there. The other one is 12.5% chance that the exposure climbs to 15 million and the probability of default climbs to 13. Remember, that was the unlikely event, so it has only 12.5% chance of happening. 12.5% chance of happening the opposite, that the exposure drops and the probability of solvency decreases. And then the most likely events, 37.5%, that exposure goes up and probability of default goes down, or 37.5% chance that exposure drops and probability of default goes up. The answer is $460,000. Okay? Very quick calculation, very short, but it gives you, I think, a sense of what we can accomplish. Very simple modeling. Very simple modeling. Okay. Now, let me spend some time with some other problems here. This I will do. Okay, I'll just do them. So here's a question: is if I give you a portfolio of 10 B-rated bonds, 10 million each, they ask you, this is a question from the FRM exam, which some of you may be considering. What is the one-year probability of default of each issuer, assuming that the recovery is 40% and the probability of default is 6%? It's very simple. You just multiply, right? It's the expected value, and it's just multiplication of those numbers. This question is really an English exam more than a credit risk exam, because you have to realize that you have to multiply not by the probability, not by the recovery rate, which is 40%. You have to multiply by the loss given default, which is 1 minus 40%, 60%. That's the only mistake that is easy to make. So the expected default is $3.6 million for this portfolio. That's the expected credit loss. All right. That's if the these are all. Well, this is the expected credit loss. Now, is that clear? Clear? Very simple question. Okay. All right. Now, this is a variation of that. I'm going to give you same portfolio, $100 million, 10 B-rated issuers, and 1 year probability of default of each issuer is the same, 6%, and the recovery rate for each issuer is the same, 40%. And what will be different this time is I want you to calculate the unexpected loss, not the expected loss, and by that I mean the standard deviation of losses. All right? We're going to calculate the standard deviation of losses, and we're going to make one assumption, which is that they're all the same issuer, so they're all 100% correlated. The other one is we're going to assume that they are independent. It's very hard to find independent credit default profiles, but I'll assume that for mathematical reasons. And the other one is 50% correlated. They're all, for example, in the same sector. There's some correlation, but not perfect correlation. So I want you to calculate the unexpected loss. I'm going to do this for you. You don't have to work, okay? But before I start, perhaps I would like to ask you, how would you position yourselves to solve this problem? The way you should position yourselves for this problem is you are given 10 random variables. Each of them has a certain mean and standard deviation. We just did that earlier. And now we need to understand what happens when you take the sum of those 10 random variables. What happens? The mean we calculated, I mean, it's easy, it's just the sum. What happens to the standard deviation of that? So what I'm asking you is to calculate the standard deviation of the sum of 10 random variables. If the correlation is 100%, it's very easy. It's exactly the sum of the standard deviations. If they are independent, if it's 0%, then it's very easy. It's the standard deviation of 1 multiplied by the square root of 10. And if they are 50%, let's do it. The loss distribution of a single random variable has two states, so default, 60 million after recovery, and default, sorry, not default, loss of 0. And so the expectation of that is 3.6 million. The variance is that, because I have only 2 events. No questions here, right? You've taken probability, you've done worse than this. Sorry, you've done more complicated things than this. That's the variance. So the standard deviation, which is the unexpected loss, is the square root of that, about 14 million. Any questions on this? This is simple. You've done this. You've done this in high school, I'm guessing. No? Not in high school? Elementary school. Grade 6? No? It's been a while. Okay, you forgot already. You said you are so young, you already forgot. All right, that's easy. So B is when they are independent. And that's easy because it's a sum of 10 random variables with each of the states. I mean, it's the same thing. Each of the states, each of the random variables can have a default or no default. $6 million in one case of loss, the other one loss of 0. The expectation is 360K. The standard deviation is 1.4 million. So the standard deviation of the whole thing is square root of 10 times 1.4 million, which is about 5 million. You've done that too. Am I wrong? Am I wrong? You've done this?
Yeah.
Okay, your faces are telling me that something is not right. What is not right? I suspect I know what's not right. I suspect is that you've never done anything as simple as this. Everything you did was more complicated. Am I right? I think that's the problem. Yeah. Sometimes courses prepare you for the very complicated things, but they don't prepare you for the simple things. And the trick is to be able to do the simple things. It's a justification for my course. That's what I like to teach the simple stuff. You can do the complicated one in the privacy of your home. Yes? This is so simple that you may find it difficult. Am I right? Okay, it's easy, very easy. Let me go to the other one with 50% correlation. There, maybe the easiest way to do it is, again, I have a random variable that is repeated 10 times. Default, no default, that's what it does. These are the individual characteristics of each of these random variables. Expectation of 360K, and the standard deviation is 1.5 million. The standard deviation of the sum is given by this expression. You know how to do the variance of a sum of correlated random variables. The expression is here in front of you. I assume you've seen this many times. There's nothing, no mystery here. And the answer is 10.5 million. Right? Good. All right, let me continue. This is simple stuff. You know that. Other problems that come from other exams. These are really. I'm going to do this. We'll take a break. Okay. So, which loan is more risky? Assume that everything else is the same. Okay. A loan of $1 million with 50% recovery rate. A loan of $1 million with no collateral. A loan of $4 million with a 40% recovery rate, or a loan of $40 million with a 60% recovery rate. Which one is more risky? Okay? Great. That's the riskiest. You knew that. Great. All right, so we're going to do a credit trade when we come back. I'm going to do a credit trade with you. It's a very simple bond, defaultable bond. It's a bond that has only two coupon payments, no principal. It pays $5 at the end of year 2 and $5 at the end of year 4. Interest rates are 0. my counterparty has an annual probability of default of 7% and recovery rate is 0. It's a very simple bond. The trick, or why this trade is going to be interesting, is when I start to introduce regulatory capital requirements. And in this case, I'm going to assume I'm not going to do a credit value at risk. It's complicated. I'm going to do a mock-up of that using the standard deviation, which is easier. Okay. In practice, you should know it's the credit value at risk, not the standard deviation. But I will use the standard deviation as a way to do that, and it will be adjusted annually. And in addition to that, there will be a certain return on risk capital. I told you, no one works for free anymore. Since reading week, no one is working for free. So this is the trade that I want to do. I would like to have 2 volunteers to do the trade. Your name?
Anthony.
Anthony. So Anthony is going to be 1, and your name?
Alex.
Alex and Anthony are going to trade. For no particular reason, I'm going to say Anthony is going to work for a bank and Alex is going to work for a hedge fund. You may not know what a hedge fund is, but you're going to learn today. Okay? So you're both going to be doing this trade. I'm going to be issuing the bond. This is the bond that I issue, and I have a probability of default of 7% per year. The question I want to know is how much you're willing to pay. Don't worry, not now. I mean, I'll give you information and then you'll decide how much you're willing to pay. Everybody understands? Okay, there's a bond, it's this one. And I am going to see how much money I can get. I'll go with the best bidder, obviously. Okay, now there will be considerations, I will give them to you, but from what you know, how much money would you be willing to offer for this bond? Well, for sure, no more than $10, right? At $10, you lose money. Yes? So we'll see how much we have to do. Let me give you some numbers. So this describes my credit quality over time. The probability that I fail, that I default on the first year, is 7%. The probability I'm solvent on the first year is 93%. Going beyond that, the probability I'm solvent for 2 years in a row is 86.5%. The probability I default on the second year is 6.5%. And so on and so forth. You can all do this. These numbers will be useful to calculate the price. Let's calculate the expected loss. There's 2 methods for that. The expected cash flow, which is what we have seen in the course so far, is $5 times the probability that there is no default in the first 2 years, because I get the coupon payment after 2 years, right? And $5 times the probability of no default in the first 4 years, because I get $5 at the end of the 4-year period. If you get the numbers from the previous chart, you trust me, the answer is $8.06.5. All right? That's the expected cash flow. So let me ask the question again to Anthony and Alex. Given that we know this, how much are you willing to pay now?
$8.06.04
All right, there you go. So that's the hedge fund talking. How about Anthony?
Wouldn't I have to discount this by the risk-free rate as well?
It's 0. No interest rates.
Yeah.
Same? Well, then if you are the same, I don't know who to go with. You have to beat each other up. Yes?
$8.06 and 4.5 tenths of a cent.
All right, well, okay. So All right, so that's your offer.
Yeah.
Do you have an offer?
I'm a bank, so I don't want to really take, like, I want it to be risk-free, so I'm not going to.
You're not going to bid.
Yeah.
Okay, well, you may have to change your mind. Okay, so I'm coming to that. I'm coming to that. I'm coming to that. I will explain today how a trader in a bank works. I will explain today how a trader in a hedge fund works. So I don't have enough information yet. Okay, in fact, you've been very generous in your offer. I don't recommend that you do it at that price. You're paying too much. Okay, but for sure, no one will pay now. I said earlier, no one will pay more than $10, right? Now, looking at this, no one would pay more than $8.06.5, because that's a losing proposition. You expect to lose at that rate. You see that, right? Yes. So we brought down the price of this trade to no more than $8.06.5. But there's something on top of this, which is how much money we expect to lose. I mean. Okay, so that's the first approach. This is, the expected loss, by the way, is $1.93.5. It's the same thing, same calculation, nothing. Now, there's a second method which gives the same result, but I'm just going to give it to you so you understand and you see that. The second method, what I'm going to do is I'm going to look at the exposure per year. The first year my exposure is $10, second year is $10, but then after, in year 3, the exposure is only $5, because in year 3 you would have paid a $5 coupon already, right? And look at this. The expected losses can be calculated. I get exactly the same answer, $1.93.5, if I calculate the exposure times the probability of default on that particular year. I mean, all the numbers that I use in this calculation appear in the previous slide. You'll have to trust me that I did the calculation correctly. I did. This is a little bit of a coincidence, and the reason it's a coincidence is because the exposure is constant. It's so simple that, in fact, the calculation on the right and the calculation on the left, they're related to each other by integration by parts. Integration by parts will take you from the right to the left. Okay? This is good because somehow it endorses our approach from earlier, where I said that the probability of, where I said that the credit loss function was the product of the exposure, probability of default, and loss given default. Remember? So this is an endorsement of that. But the fact of the matter is that I get the same answer, $1.93.5 in both cases. All right, good. It still does not address the question. It gives you a better compass to make a decision. Now we know that, about $8 is what you're willing to pay. But now let me look into the unexpected loss. The answer to this question is in the unexpected loss, because imagine the unexpected loss is very high, very, very high. When you want to pay $8 and $6 and 4/10 of it, way too much, because, right? If it's a very risky event, if there's a very high probability that you will be paying more than that, then you're going to lose money. So even you, the hedge fund, will have to take the unexpected loss into account. You have to somehow factor the standard deviation into your calculation, right? All right, good. All right, now what I have here is the way you would do the standard deviation of losses per year. It's just a standard deviation. I apologize, the formulas are so complicated because there's a lot of terminology, but you all know standard deviations, yes? So you can do the standard deviation per year. There's nothing secret here. And the answer I get is that, well, I have the variances, is 6.5, 6, 1.42, 1.33. These are the variances, which give me standard deviations given by this. The first year, the standard deviation is 2.55. The second year is 2.46. The third year is 1.19. Of course, I've already received the first $5 payment, so it drops substantially. And then $1.15 for year number 4. These are the standard deviations. And this is where things get interesting. Because once I have the standard deviation, then I can start to I have more information about the risk involved in this particular trade. Now, I have to say one thing. I've said it several times today, and I'll repeat it again now. I'm using standard deviations because they are easy to calculate. Credit value at risk is typically more complicated to calculate, but that's the one you would use instead of standard deviations in a real situation. The only reason I'm using standard deviations is because they are easier for class. But when you're doing this real trade, it doesn't matter. You don't do the easy, you do the right thing to do. But today I'll do the easy. Allow me to do that. So if that is a good description of the risk I have, then I can go back to the question, what would you pay, what would you pay, right? There's no infinite risk, so even a bank would have some sort of a idea of how much they're willing to do. But I'm gonna give you the formula, not you.
Okay.
Because you are a hedge fund, you're a private corporation, but you are a bank, you're a regulated entity. So I'm gonna tell you how you are regulated, and then you make your decision. You're not regulated. So whatever, if your investors are happy that you take risk, you take risk. If your investors are happy that you pay $11 for this bond, you pay $11 for the bond. You can do whatever you want. But for you, no, things are different. A regulated entity and an unregulated entity, things matter. And this is a course on credit risk. And credit risk involves trading that applies to everybody who wants to enter into the market, everybody that wants to issue or buy a mortgage, for example. But then the regulated credit risk as a measure of controlling regulated entities like banks, is also related to this, and I want to address both. So in this example, what I would have is the following. Imagine for a bank, if I'm the central bank, I want my banks to take risk, because they have to be profitable, but not too much risk. And the way I control that is, I look at the risk you take. Normally will be done through the credit value at risk, but here I'm going to do through the standard deviation, which is easier to calculate. And I want to say, do whichever trade you want, pay whichever amount of money you want, but 2 times the standard deviation becomes regulatory capital, in your case, right? So if you go back to the previous slide, I remind you the standard deviation for year 1 was about $2.50. Which means that $5 you have to live with me, the central bank, for 2 years. After which, I return $2 to you because the standard deviation dropped to about $1.50, so that's 3. And then I return $2 to you, and when the bond is done, after 4 years, you get all of it back. But there's regulatory capital coming from you. No regulatory capital coming from you. Do you understand that? That's how banks work. Banks have regulatory capital, you don't. This is money you get back, but it's money, no one works for free. It's money that removes profitability, as I'm about to explain, so you will understand. Yes?
So just a quick question, like why are we assuming like discrete time? Like, why are we assuming discrete time, like for time intervals?
Discrete time in...
Like for defaulting. We are assuming like the time for defaulting is a particular time. Like,
So I don't understand your question.
So we are assuming like the times are intervals, right?
Time intervals. Time interval.
So I just.
You mean for my standard deviation?
No, I mean, what can you just like model it with a gamma distribution? Like
With a so what do you want me to model with a gamma distribution?
Like the survival time.
The survival.
Yes. Like should I be able to model
The okay, so I'm assuming I'm just giving the probability of default, right? It's 7% per year. If the probability of default is 7% per year,
like why per year? Like why don't you set it like continuous?
because the probability of default is typically given on a, it doesn't matter where it is, but I look at the probability of default on a per year basis, right? I can look at the, no, I think we saw last week that I could give you the Kolmogorov infinitesimal generator, and it's exactly the same thing, right? So if I can go from per year to per month to per day to per 5 years. The amount of the time interval I pick is not relevant. What's relevant is the credit model I follow. That's relevant, but not the probability of default, right? Okay, but I'm not sure if I understand your question. I did? Are you sure? Okay, I'm not sure. I think there's something deeper into your question, but I failed to understand what it is. Okay, that's okay. I'll continue, and then if anything, then I can address it again. All right. Okay, so this is the regulatory capital that the bank will have to put aside. You're going to get it back, okay? But you have to put aside 510 for 93. Then this is the standard deviations of that I calculated earlier times 2. Now, this is very. I want to talk about something else. Yes.
Clarify. So what happens between year 0 and year 1 is they will return like some amount of money, like they'll free up a certain amount.
Right. Yes.
Okay.
Yeah. You would typically do this on a daily basis. So the banks, they have a calculation of regulatory capital every day, and that's what they negotiate with the central bank, right? That's what banks do. And in fact, for those of you who end up working in the banks in the credit area, most of you would be related to something like this. Some of you would be actually calculating these numbers. Some of you will be, like in your case, subject to these numbers. In the bank, you have, well, there's many different departments, but they said that the trading department, you do the deals. You are the one who says, "Oh, I like this bond. I want to buy it, and I really want it because it's a great deal," right? And that's, you can say, "I don't want to do it," like you said earlier. But if you never do anything, then you're not going to make any money. Right? You have to take some risks, but the risk will be controlled by the credit department. So some of you in the credit department are the ones who will be, if you follow my metaphor, you will be the ones that calculate this number 5.10. That's your job. And your job as the trader is someone say, well, when you do this deal and you're given a P&L, you have $100 million in the P&L, right? This is what you can trade. Say, damn, I'm gonna buy this bond, but I buy this bond for some money, and then I have to say that you pay $8 for the bond. Then according to you have to give 5 to the regulators. So the 8 you pay plus the 5 you give to the regulators, that's $13. You're gonna get it back, but not until 4 years, right? And now I go into another topic that I want to bring up. This is really related to what we'll be talking about next week. Next week, I'll talk about investments. So it's related to what we'll be talking about next week, which is that when you do a deal like that, the bank will charge you money on the P&L. Let's say that you have $100 million, as I said earlier, for your that you can trade. Well, that money is not for free. That money is something that the bank will charge you for that. In this case, I'm taking a charge, it's very high, it's 10%. Usually it's 5, okay? But 10% is very high, but it's easy to multiply by 10. So that means that when you give the regulators $5.10, it actually costs you 51 cents of real dollars. You lose that. You have to make up for that with another deal. Otherwise, your P&L will go down. You lose, and then, well, that will affect your bonus, perhaps. Understand that? At the end of year 1, you are returned 23 cents. And in year 3, you return a lot of money, more than $2.50, right? But that will cost you, in this particular example, 10% of that. It's real cost to your profit and loss. Your performance will drag by 10% of that. You don't have that. You're a hedge fund. You don't have to submit any regulatory capital, right? But you have investors to report to. If you take a lot of risk, your investors may care, but it's your decision. You can overpay, right? So this is now a bit of a, oops, sorry. I need to, So when you add all of the regulatory capital that you need, assuming 0% interest rates, what that ends up being is, for you, the bank is a surcharge of $1.47. You don't have that. But let's say that you worked in a bank. You know you can do these calculations yourself. So what is the most you can pay for this bond? The most you can pay. Yeah. So the most you can pay is $8, and what was the number? I forgot. You have it's $8 and something, right? $8 minus 147. That's the most. You cannot pay more than $6.50. If you pay more than $6.50, you're actually losing money. And I'm not saying you're losing money with a probability. No, you're losing money, right? So you're gonna pay $6.50. You cannot pay more than that. How about you? Well, what I would do is I would pay $6.51. That's what I would do, right? Because you know he cannot go to $6.51. And regulate it, and then that will give you a rate of return that could be competitive. And then you show up at 651. You cannot go to 60. You go home, and then I give it to you. You understand this? Now, what's to understand here is many things. Today, what I want you to understand, we'll do a lot of investments next week. So that will be, a lot of these things will become more fluid. But for today, what I want you to understand is the impact of risk management in his ability to trade. Risk management will make you less competitive. It also makes you safer. And since banks are systemic to the economy, that's why banks are regulated. Let's go back to 2 weeks ago when I gave you the history of risk management. Remember that? I told you about this one event that happened in the year 1998 when long-term capital management blew up. Banks were not regulated in how they could lend to customers. That happened after that. So what I'm telling you here, the metaphor of what I'm telling you here happened because of that. So there's a limitation on the risk taking that banks can do. Okay, that's what I want you to understand from here. There's lots of other considerations about profitability and this and that. We'll defer that to next week. Today, I want you to understand the impact on risk management. All right, clear? Good. So what I'm going to do now is I'm going to, the last hour, I'm going to talk about the commercial credit risk models that exist. Now I'm going to become very, very commercial. I'm going to show you how these things are sold. The first one is one called CreditMetrics. It was in the history of risk management that I gave you 2 weeks ago. It was done by JP Morgan in the year 1990, essentially 1998, although it was done a little bit before that. And in this one, credit risk will be driven by movements in bond rating. So it only applies to companies that issue bonds. And credit events are downgrades with a transition probability matrix like we saw last week. So it's a Markov chain model. Credit matrix is a Markov chain model. And each instrument is going to be analyzed through the credit spread for each rating class, for each state in the Markov process that we have. Recovery rates are obtained from historical similarities. So there's nothing deep about recovery rates. I want to show you 2 calculations that I did for CreditMetrics from where you can extrapolate how it works. I don't have time to explain all of it. I just want to give you a summary of that. And I want to show you how correlations are done, but I will show you the actual example of that. And something very important, it does not integrate market and credit risk. It's one of the things that makes it work. I have an example to show this. Imagine I have a bond rated BBB. And what I have here is the transition probabilities of BBB to any other rating. So they say a 2 basis point chance that it goes to a AAA. They say a 1/3% chance that it goes to a AA. There's a 6% chance it goes to A. And then there's a 5% chance it's downgraded to BB. A 1% chance it's downgraded to single B. a 12 basis point chance that it's downgraded to triple C and an 18 basis point chance that it defaults. Okay, it's just given. This, I remind you, this is what the credit agencies sell you. This is part of the transition probability matrix that is sold to you. That's going to be my input. I also know, this is what's new, that depending on where the bond goes, the value of the bond will be one thing or another. If it's upgraded to AAA, that the value of the bond will jump from 107.55, which is where it is now, to 109.37. It'll get better. That'll be a credit gain. That comes from an upgrade in the credit quality of my counterparty. We're more interested in the losses. And the losses is what happens when it gets downgraded. And I have here the examples for you of the values of this bond when it's downgraded. And then you can do statistics. You can do the mean, you can do the standard deviation. But I'm going to be interested in neither of them. I want to be a bit realistic now, and I want to do the credit VAR, credit value at risk. Okay? You would know how to do the statistics. We're past that. So to calculate the credit value at risk, I'm going to do a table, which is the loss event and the probability of that loss event. The first one is I can lose $56.42. That corresponds to my default. Note that when the bond defaults, the value is 51.13. That's the recovery rate, right? It's built into that. And there's an 18 basis point chance that this happens, and then the loss would be $56.42. 56 is 107.55 minus 51.13. There's a 30 basis point probability that is downgraded to triple C, in which case I will lose $23.91. And it's downgraded to B with a probability of 1.47. That's 945. 553, and that is how the default curve is going to be for how much money I lose with what probability. Right? That's my loss function for this particular bond, with the transition probability matrix given by the rating agency and with the market values of the bond that I observe in the market. Yes? So from there, I can see that the worst credit loss of 95% is going to be about $10. And the worst credit loss of 99% is going to be about $20. The credit VAR is very similar because the expected return is about zero. You just do it. It's very small. So in this case, the worst credit loss, the expected loss is very small. The credit VAR will be a little bit smaller than the worst credit loss, but you understand, once you have the quantile, then you just subtract the mean. All right? See that? So that's how you do this in the context of credit matrix. And it all hinges on the Markov chain sold to me by the rating agency. Is this clear? What if you have more than one bond or more than one counterparty? The same, you just add it up. You add up, and then that becomes a simulation exercise. So you need to have now a simulator. So this becomes a type of Monte Carlo simulation. Yes? All right. Now, the difficulty when you have more than one counterparty is in the simulation is not so much what happens to each of the instruments that we already saw what's there, but what happens to the correlations. We already saw the correlations are significant. We saw two examples. So how do I correlate my counterparties in this case? So they give you a recipe, and this is a recipe. There is no theorem, there's no math, it's just a recipe. I'll give you the recipe. And to give you the recipe, I'm going to use an example. Let's see that my counterparties are DuPont and Allianz. DuPont is a plastics manufacturer in the United States, and Allianz is an insurance banking enterprise in Germany. Let's see, these are my two counterparties. How do I find the default correlation between them? By the way, I hope you know why I'm doing this. If I have So what I did in my previous table is I showed you how to model one instrument with one counterparty. Many instruments with one counterparty is just an addition. But when I have my counterparty simulation, my other counterparty simulation, how do I put them together? It's like the correlated coins. I need to know the correlations, right? That's what we saw earlier. Understand? I need to know the correlations. Once I know the correlations, then I can model them. So the correlations are given by the following method. It's like a cooking recipe. There's no reason to do it like this, but this is how it's done. These credit rating agencies not only sell you the Markov chain, they also sell you things which are indices of different types. I'll show you what's relevant in this case. And in particular, there's something called the US Chemical Industries Index and the German Insurance Index and the German Banking Index. They give you that. These are just time series of performance. Where they come from, you don't care. You just use them. It's a recipe, okay? And you do a regression between the stock returns of both DuPont and Allianz, your two counterparties. And you get a regression result, something like this. In the case of DuPont, you get a 90% beta to the US chemical industry, plus some white noise. And in the case of Allianz, you get a 74% beta to the German insurance index and a 15% beta to the German banking index, and some white noise. You do this regression. It's a recipe. There's no math here, just a recipe. And then what they say is, they say, well, then the correlation of default from these two counterparties is given by the product of the betas times this thing called the correlation between indices. It's also given to you. It's part of the recipe. You just use it. There's no mathematical meaning for any of this. You do the product of the other betas together by the new default correlation index that you have here, also given to you, and then you just do the calculation, and the answer is 11%. This is a recipe. There's no math here. There's no way to prove, to justify this or anything like that. Amongst other things, as indices do not default. These are just numbers in a matrix, which is sold to you as part of your subscription. You understand what I'm saying? This is a very interesting use of mathematics. I told you how 2 weeks ago, I told you how important it was that when mathematics was brought into law. Well, when mathematics is put into a software package, it's important too, isn't it? And that's what we see here. But it's important to say that these are sold numbers. They are not calculated numbers. The recipe, you just follow them. Okay? Don't ask me why. This is in the CreditMetrics methodology. There's no answer to why. It's rooted in some mathematical thinking, but there's no mathematical justification for this. Now, when you have more than one counterparty, now what you have to do is you know how to simulate one counterparty, and now you have the correlations to do it between them. Now you simulate all of them together. So if you have a portfolio of m counterparties and a total of n possible credit states, for example, 8, then you need to simulate a total of n to the power m states. How much is that? How many counterparties does Scotiabank have in Canada? Let's say 1 million. So that'll be 8 to the power 1 million, right? Yeah? You know how to do that? That's where another type of fun begins, something I'm not going to address here. But we can look out the window. You see what type of massive simulation this is going to require, right? Yes? I'm going to say nothing about that. Nothing about that. Of course, of those 8 to the power 1 million states, maybe not all of them are very relevant, maybe some are. And then mathematical considerations become really relevant. Which ones do you simulate? Importance, sampling, this and that, right? But that's a whole new territory that I'm not going to even touch. I just mentioned. The thing to know is that we have the marginal distributions and we have the correlations given by the regression model. So in principle, you can build a simulator using very smart programmers. All right? And then you will obtain, hopefully, meaningful results. The problem is that when you do these simulations, what are you simulating? You're simulating the tail of a distribution. So let's say that you're trying to simulate for the 99% credit value at risk, or the 99% worst credit loss. What is that telling you? If you simulate to calculate the 99% worst credit loss, that means that for every 100 simulations, only one matters. Right? Only one matters. So by design, these are very time-consuming, very difficult simulation challenges. And I leave it here. I just want you to understand how difficult these things are, okay? And to make matters even worse, this does not take into account that markets move. It only considers that credit counterparties move. So to do it properly, you need to integrate market and credit. That's extra difficult. And we'll stop here. I cannot go beyond this. That's a whole new course to go beyond this, to go even a few inches beyond this. Now, there's a different approach, and that's what I want to end with. The different approach is a theoretical approach, but very, very useful. It's a type of approach that was brought by Robert Merton. Robert Merton, in the year 1973, was working on the problem of solving the pricing of an option, something that Myron Scholes and Fisher Black were also working on, and they obtained the solution that we showed here. Merton was working on a different solution that he did shortly after. Okay? In his approach, which for credit, which he did in 1974, the Black-Scholes formula is from 1973. So that, as you will see, that was needed to do this model. So in his approach, in Merton's approach to credit, he did the following. He said, and this is an accurate description of how counterparty happens. He said, when you have a credit-prone counterparty, a company has assets and liabilities. Equity is the difference between assets and liabilities, as you may know from accounting. So default will happen when the value of the assets is less than the value of the liabilities. That's when default will happen. That was his argument. So we'll model the assets, we'll model the liabilities, and in that way we'll model default indirectly. But what's interesting is that if the value of the equity is the difference between assets and liabilities, equity is never negative. So equity is really an option, a call option of the value of the assets with a strike price equal to the value of the liabilities. A company has the right to default. That existed since the Industrial Revolution. The corporate law allows for bankruptcy. That means that default is an option that every company has. From Merton's perspective, that optionality is built into this definition of what default is. Actually, it's built into the definition of what equity is. So equity is the value of a call option, where the underlying is the assets of the company, and the strike price is the value of the liabilities. You understand what I'm saying right here? Do you understand that? We typically talk about options as the underlying being a stock price. We haven't talked about the stock price being an option itself, where the underlying is something else. I'll give you an example. Air Canada. What is Air Canada? From this perspective, Air Canada is some assets airplanes, and some liabilities, what they borrowed against the airplanes. If at some point the value of the airplanes is less than what they borrowed, they can say, oh, there you go. I have no obligations. That's a call option. Because if the value of the airplanes is more than the value of the liabilities, well, that's your asset. That's what it's worth. But the value of an option is not the intrinsic value. The value of the option is not the value of the stock minus the strike price. It's higher than that. We saw that. In fact, we developed the Black-Scholes theory to do that. That's why Merton was developing this theory, so he could do his credit risk model, which is the one I'm going to show you now. Because now we can not only model default, we can model bond prices under default and lots of other things, as you're about to see. I want you to understand the premise, the financial premise we're making when I say that the value of a company is a call option, where the value of the assets is the underlying and the value of the liabilities is the strike price. And default occurs when the value of the debt is higher than the value of the assets. And from this perspective, the equity of a company is an option of the assets of the firm where the liabilities is the strike price. So let's follow our nose with this assumption. And that means that the equity can be modeled as the maximum value between the assets and the liabilities, assets given by V, liabilities given by K, and 0. So if assets and liabilities, if assets are less than liabilities, then you just default, the value of the equity is 0, never negative. Since the firm's assets equal the value of the bonds plus the equity, you can model the bond prices as the value of the assets minus the value of the equity, which is that maximum value. In other words, is the minimum between the value of the assets and the strike price. That's what the bond value is. And this is another option. So Merton is telling us that both the equity as well as the bond itself are options. And the bond is like a short put. The asset value is there, the stock price is there, and the bond price is there. The stocks are a call option, and the bond is like a short put. Yes.
I was just wondering for the max between 0 and UT minus K, what if this financed by equity, and then perhaps there's more equity than there is.
Then you would never default because you don't have any liabilities to anybody.
Oh, because then the equity form value.
Yeah. If you have no liabilities, then you would never default, right? But I mean, liability debt is just one form of liabilities, right? So imagine you have payroll, you have things that you owe, all of that will be liabilities.
That could be a liability.
No, well, okay. Equity is a residual liability because a company needs to have 0 value. So equity is what the company owes the shareholders. So yes, equity is a liability to the shareholders from the company, but it's a residual liability, is not really a liability. Yeah, it's not a liability that will trigger a default, all the opposite. Right? Yes. Okay. All right. So if we assume that the firm assets follow a geometric Brownian motion, like the one we have seen here with the Ito process, then we know how to price the options on that, right? And we have the Black-Scholes formula that we saw a few weeks ago. I'm not going to go through this formula. It doesn't matter what these things are. We already saw it. I'm just going to show you that these things actually exist. They're going to come up in my derivation, and I'll tell you what they are as they come up in my derivation, not now. And so I have a way of understanding what the value of my equity is from the Black-Scholes perspective. I'll come back to this in a minute. What I want to say is that in this formulation, I need the volatility of the assets, not the volatility of the stocks as input. The volatility of the assets are very hard to calculate. The volatility of the stock, I could. We have implied liabilities, we have historical observations, historical time series that lead to calculated volatilities and so on and so forth. But for the assets, we don't know. What's the volatility of your airplane valuation? I don't know. And if you make the assets very complicated, then we don't know. So this is the interesting part in the Merton model, which is we will have to figure out how to calculate that. I will show it to you in an example. It's a very interesting algorithm. I'll show you. But it all comes back to Ito's formula, because the hedge ratio is the relationship between the equity as an option and the asset value as an underlying. And they are both related by this derivative, which means that the volatility of the stock and the volatility of the assets need to be related by this formula. And this formula, it is, you could say, oh, then that's easy. I know the volatility of the assets. I just take it to the other side, I divide by this and this and that. The thing is that, well, no, because everything in that expression is a function of the assets, and everything is a function of the volatility of the assets. The fact that you see the volatility of the assets, sigma V there, does not mean that that's the only place where it occurs. It's in the delta, it's in the ds by dv. It's in V, it's in the value of the asset. Sorry, it's in S, it's in the value of the stock, right? So it's not just there, it appears in other places. So this is equivalent to a fixed point expression. We're going to see two fixed points today. This is a fixed point expression. Knowing that everything on the right is a function of the volatility of V, then the volatility of V is that number that if you plug it into the right-hand side expression, gives you back the same sigma V. That's what it is. And I'll show you how this is done in practice. It's very simple, very simple. For that, I'm using the one option calculator. Here I use the option calculator done by Professor John Hall from Rotman, which comes with his book, and it was available for download on his website. I don't know if it's still there. It doesn't matter. There's millions of calculators of options out there. I still use this because I like the graphics. It's good for me to teach this. And I will show you how I have to misuse his calculation, his calculator. Okay, because the calculator is developed to calculate prices of options and equity. But here I'm using this to calculate the equity as an option on assets. So where it says equity, I have to put assets. I have to misuse it. Okay, but I will show you. That's what I do. So I did this for Goodrich, and for Goodrich, what I did is I go back to the stock price, and the stock price is what? I'm misusing this. By stock price, you see there, by stock price, maybe I write here. I'm going to show you how I'm misusing this calculator. You'll have to misuse it when you use this. Oh, by the way, you have to do this as part of assignment number 2. I'll tell you that when I finish, okay? So you have to find a calculator and you have to misuse it too. I'm going to use a color which is different here. You see there, it says stock price. Well, that's not the stock price, it's the value of the assets. Because in this calculator, stock is the underlying. The underlying are the assets. And the assets for Goodrich are $6.8 billion. I'm using all of this information from, I'm doing this for Goodrich, so I have to get this from the financial statements. Okay, you have to do this from the financial statements of a company. Once I tell you what your assignment number 2 is going to be, you have to do this. Okay. The volatility is what we don't know. But what I do, you will see, is I just put the volatility of the stock. It's wrong. I put it there. It's wrong, but I'll fix it later in a way that I'll show you. So that's that. And then I put the risk-free rate of return. That I know and that I need. And you have that because you get it from assignment number 1. So you put it there. So this expression that we have here comes from the financial statements and the volatility, which I have to guess. And I'll show you how I do that. Then I look at the time to exercise, which is a year. And the exercise price is what? Is the value of the liabilities, is the future value of the liabilities. That's what the Merton model tells me it should be. And then I hit calculate. Oh, by the way, I do a call, not a put. And then I hit calculate. When I hit calculate, what do I get? I get the price. That's the price of the option. That's the price of the stock. in the Merton model. And I also get the delta. The delta I need because the delta goes here. And then I go to this expression here and I calculate this from the calculator, this from the financial statements. The delta comes from here. I multiply by the volatility of the stock that happens to be 50%, but I multiply to whatever that number is, and I get an answer. You understand what this process is? And I get an answer. When I get an answer, the answer is 14.77%. That's what I get. I get 14.77%. But then I go back and I put it there. I put the wrong volatility earlier, 50, because I didn't know what to write. Now, I'm going to put the obtained value. For those of you who know fixed point theories, you would know that this is very typical how you find fixed points. You just iterate, right, until it converges. So I plug it in there, and then I redo the calculation, and I get a different value for the value of the stock and a different value for the delta. I put it back, and guess what? I get 14.77% again. So what happens when I take 14.77% for my input for the volatility? I put it into this expression that we have here, and I get again 14.77%. I have arrived. That gives me the volatility of my assets. Okay? Yeah.
You solve it as a differential equation.
That's what I did. Essentially, that's what I did. Okay, but I gave you the fixed point theorem that will get me there. Yeah. So this is good because with this, with the volatility of the assets, I can find what? I can find the probability of default of my, oh, by the way, this is what a fixed point is if you've never seen it. And the way to find a fixed point is very often by iterating. Sometimes they converge. Different class. Okay, is that clear? So I can price the equity, but now let me price the debt. The debt is the important thing to price because from pricing the debt, I can find the probability of default, which is my objective. So the value of the bond is V minus the value of the equity. The value of the equity, I use the Black-Scholes theory, and then I get a Black-Scholes version of the value of the bond, which is this. And I'm going to rewrite like this. I want to rewrite the value of the bond like that. I divide the value of the bond by K and the exponential of the time to maturity or the time to default. And I get an expression like this. This comes from the Black-Scholes theory. And here there's a miracle that happens. I want to explain it to you very quickly. The miracle is the following. The Black-Scholes theory will tell us that this number that I called ND2, that we've seen now several times, happens to be the risk-neutral probability of exercising the call. Now, exercising the call means no default, right? So that means that the ratio between the bond and the risk-free value of the future liabilities is essentially the probability of no default. But we saw that expression already. When we studied sovereign default last week, right? Remember that? The difference, why? But now we have that junk over there that goes with the probability of no default. What's that? Well, that is the following. The Merton model not only gives us the probability of default or the value of the equity or the value of the bond, it also gives us the recovery rate. Let's think about that. How does it give us the recovery rate? What is default? The value of the assets is less than the value of the liabilities. But what do creditors get? They get the difference. And that's modeled by the Black-Scholes equation too. You see, the Merton model is very interesting because it has built in the recovery rate. Understand what I'm saying? The recovery rate is the value of the assets minus the value of the liabilities. That is the recovery rate. That's what you get back. So I don't have to model, I don't have to say it's 50% or 30%. Whatever it is given by the stochastic process. And that's why everything we saw earlier is revised to take into account the stochastic recovery, because the Merton model is a model for stochastic recovery. Okay, I don't know if I'm losing you now, but if you understood everything we talked about until today, I'm happy. Okay, I just want to show you a second miracle. When I calculate the expected credit loss, that's the difference between the risk-free rate of, between the risk-free bond and the defaultable bond is here. And when you do that, well, this is the expression using the Black-Scholes equation. And again, because of the Black-Scholes theory, that number is the probability of not exercising the call, which is the probability of default. And then what you have inside is the exposure. Well, the exposure clearly is the first term. How about the second one? Well, there again is the modification, is the revision needed because there's stochastic recovery that the Merton model gives us. All right. That's the present value of the value of the bond, and that is the modification that arises from the stochastic recovery that the Merton model gives us. Now, the thing that in practice, these things are extremely easy to put together, because what the Merton model does is says, well, let me evaluate the value of the assets. They move as a stochastic differential equation. I have a default point, which is the value of the liabilities. Everything above that is what the company is worth, and everything below that will give me the recovery from my bonds. So I can calculate the expected default very easily from this model. This model does not, note that it's not, it's a model which is, it only has two states, default and solvency, but the probability of moving from one to the other is not constant, it changes. So it's not Markov, it's Markovian of a different type, where I don't have a Markov chain. It's the probability that changes. But there's a very simple way to calculate expected probabilities of default, because what you do is have an example here. If I have a company, I'll show you the example I'll show you how it works in a particular example, okay? KMV is the commercial version of the Merton model. So KMV and Merton are the same for us here. If I have a company with a value of the assets equal to 500 million and liabilities equal to 300 million, and the volatility is 100 million calculated like we did earlier, then you just look at the difference, assets minus liabilities, that's 200, divide by 100, that's 2. And then you look at the cumulative distribution of the Gaussian at 2, and you get the answer of the probability of default, happens to be 2.3%. That's how easy this thing is. Okay, it's a very simple application of the Merton model. Okay, I end it here. I want to spend now a few minutes talking about your assignment number 2.